report now, and Vasily Mikhailovich will welcome everyone before his report. Dear colleagues, I would like to tell you about some unique technology based on serious fundamental ideas. It's about welding mixing. It's a technology that we started to develop in 2012, and now our team is in top 25 world developers. Before discussing some fundamental things, I would like to tell the following. This year there was an essential event. A pattern was weld of the rocket Soyuz 5, and this corpus was a participant in the process. And so this welding is installed. We would like to also note that the scientific input in different branches of mechanical engineering is on the third place, which is proved by having a lot of resources that are necessary to observe, to study new technologies. I would like to talk about welding with friction and mixing. It's a process which happens in the solid state when the instrument, due to the heating of friction, mixes and different processes are occurred. The welding itself has advantages. First of all, it helps to weld such materials that are not possible to weld. Unless it's welding with mixing. And in this case, we can see the equal strong connection, which doesn't give any defects. And this technology allows to have stronger conjugation. Here you can see the peculiarities of welding, where a cooler is formed. And there are different zones where the welding brings. In the picture you can see the work of instrument, which goes to the almost whole width of the material. And there are different methods which bring to a variety of results. This welding allows to weld width until 50 millimeters, sometimes reaching 100 millimeters. Here the instrument for welding high width is shown. What is important in welding with mixing? Um, many many manufacturers identify three parameters: rotating frequency, with big loads, we receive a big variety of parameters, but big loads need huge equipment. As an example, in 2013, at the factory Полет, they they got an equipment for producing As an example, you can see an ordinary seam. There can be different resistance of the material. You can see different channels of different particles that were unsuitable for it. Concerning the seam itself, in the seam, we can see the improvement of parameters, and usually the core of the seam is way stronger. The same concerns titanium alloys, copper alloys. I would like to pay attention to the process of friction welding with mixing. We have an instrument which layer by layer goes in the process, and if the strength of friction is too small, we won't come to the necessary result. If we want the instrument to get the material, first it heats, then it obtains, because in the process it becomes stronger, and at definite depths it moves and the material also moves, as we can see on the material itself. So these are the one of the main mechanisms. The next step is the fragmentation of the material. Then a solid material is made, and further the layer by layer it is connected to each other. And as the material is clean, a seam is formed. I would also like to add the following. It's very essential to understand what repeated movements give. For example, to re-weld it, in the picture it is shown that the next entrance needs some changes. When forming new materials, one seam can get through another seam. The next mechanism is about the ones that happen due to heat influence. Both thermal and mechanical influence are responsible for particle absorption, for crystallization. Now you can see different angle of the same scheme. You can see the static recrystallization, growth of grains, and in terms of high temperatures. What concerns this mechanism, they are more generalized here. The particles of secondary phases undergo different stages. These particles are cut with the help of dislocation. Sometimes they get absorbed, melt, and we have studied the morphology and even defended a candidate dissertation about the work of these mechanisms. Moreover, the materials can be quite different, and we undertook such research. They can form various things. They can divide into secondary phases. We can also see alloying These are the more generalized mechanisms, and the interaction of the instrument with the material is quite essential. The instrument can be worn in the material, which is obvious. And the form of the mixing zones can be deformed. Also, as the instrument usually interacts with the material, different processes of diffusion are included. Due to these, different layers are formed on the surface, which can be distracted and then formed again. We consider, when welding the aluminum alloy, the formation of intermediate layer is formed, which further can be also distracted. We have melted different alloys: titanium, steel, aluminum, and of course we understand that depending on the metal, different instruments can be used and should be used. Basically almost always we can see the specific type of instrument which should be paid attention to. Now you can see the list of different mechanisms which are undertaken at different processes while using the instruments. All these mechanisms are related and the mechanism give the correct choice of usage of parameters. So in fact, it should be understood how the material behaves itself and which instrument is suitable for it. You can see a huge equipment which is worked in factory progress in Samara. Thank you for your attention. So first of all, the main problems for solutions are not about thermoelastic alloys. If we take them, we get a seam which is quite strong, but because of heating, the layers around the zone are stronger. So what we get is more than 90% of elasticity, and different approaches have been used. For example, the influence of ultrasonic effect. So a strong ultrasonic uh, is applied to the material, which gives less thermal energy but more plasticity. Have you have you ever tried to weld the materials like titanium and steel, which can be welded in an ordinary way? Have you ever tried to do that? We have tried to weld titanium alloys as well as aluminum and titanium alloys, which is practically more interesting. In fact, in this definite case, we don't really need some other materials. We can see different intermetallites, which don't make the seam stronger. So it is welded. How do you choose the parameter properties? So I show the defects which can concern. At the very beginning, when we started working with welding by mixing, we had to understand what failures can occur, and we have gone through various different mechanisms to understand which brings to defect of the mechanisms. To avoid this, we can see which properties lead to it, which don't. Many can think that it is done only with the help of intuition, but in fact it's all about a huge work experience with welding. So as I understand, everything can be melded. So are there any problems when processing? Yes, of course, there is an issue with the equipment, which is uh, very costly, and we need about 3 tons of pressure. Concerning physics, the main problems, especially talking about different properties of materials, when the instrument works with a softer material, there can some problems occur when the elasticity of the seam becomes too weak. So there are several restrictions that should be taken into consideration. And we can also mention that the international standard of welding by mixing was formed in 2011, and in Russia it appeared only in 2020, and there is a lot not studied, and there is a lot of space to work and work. One more problem here is in the instrument. To weld the titanium alloy or steel, we need temperatures about 1200 degrees when the materials are mixed properly. And mainly it's very hard to find such materials. And when we weld titanium or steel alloy, we weld not the whole width, but only part of it. And the material, being fragile, can be crushed easily. How do you find the connection between the parameters of deformation and the formed microstructure? Do you use modeling in order to connect the joining of microstructure, the process of welding, and how do you define the temperature in the zone of welding seam? Concerning the first question, we made attempts to work with modeling of the process, which is quite hard. In our team or in the institution, there is a lot to do. Concerning the temperature control, of course, we control the temperature, but it happens by implication. Mainly the absolute temperature is not as attractive, as we need to mix the materials properly. And for that reason, there are different characteristics. So we didn't measure directly, and it can be from 400 to 500 degrees. Thank you for your attention. The next report, Vasily Mikhailovich Fomin. The report, the topic of the report is defining of strong characteristics of nanosized of nanosized fillers through modeling homogenesis. First of all, as young people say, what was the reason of making it, doing it? First of all, it's about physics. There are many arguable points, and there are many nanomaterials which are used in different materials, such as steel, and we obtained a very attractive result. You can see the relative Young module, and the mass concentration. So the problem has existed about 50 years, but nobody has answered the question yet. So what is nanomaterials? Based on the book by Kozlov about basics of plastic deformation and nanostructural materials, you can see different sizes. Small sized grains, ordinary, regular grains, and big sized grains. We invite the colleagues of the Institute to study this topic. So what I'm coming back to the topic. It's about the measures that we are going to look through. There are you can see the radius and the sigma E. you can see how to receive material. If the sizes get a bit smaller, you can anyways get good patterns. We observe the growth according to the whole patch law. You know all this formula. And the next step, we can see a very big measurements and where it starts from, where the sharp growth starts from, in order to include it into the parameters. So burn blood got into this area to consider the mechanic of continuous body. What is interesting, if we take the pyramid parameter, so the parameter beta, which is the distance between radius divided into this characteristic, it equals to 3.13 approximately. So if this parameter is very low, then you can't use the classical mechanism of continuous areas of continuous bodies. So this in these borders you can see the understanding where we can use where we can apply the continuous body mechanisms. In the reports of Russian Academy of Science by Utkin, we can see the dynamic molecular dynamic approaches and the coefficient of module elasticity was counted. So you can see steep growth after the 15 in the left picture, after 8 in the right one. There are many different methods. We have once won the grant, and you in the magazine Physical Mesomechanics you can find this work. There are many links, and everywhere um, everywhere we have low accuracy being responsible for it. You can see different phases and parameters according to these phases. And all these parameters will be included in them. We can define these parameters of nano-sized materials. There are many different ways of homogeneing. There are methods of average out. We have taken the simplest in order to undertake the experiment. In order to get these characteristics, we need to go through experiments, and we need this experiment be very factual and simple. So we can see linear tensed condition, and if we have the results after the experiment, we can obtain what we wanted to. So the average parameters according to one-dimensional conditions, and you can also see the tensed deformed conditions. So in order to have generalized average, you need to have different states of the material. So the phase included into this material also depend on these equations. You can see the first phase and the second phase, and So the equations are presented here. You can see when summing up these forces, you can see as a result we get equation. We get an equation of balancing state. Let's imagine that we have the following case. The tension related to the average one and the local tension is presented as a sum, and the deformation is also related with this formula. When conducting the regulations of saving, so when the average Young model and different coefficients, you can see the first equation and the second one. The first one was got for tensed state and the second for deformed state. At first sight, these equations can seem quite simple, but in fact they are not. The second case considered is about the tension connected with volume concentration. Here we apply mechanically. In this case, you can see now if we solve this equation system, we can see the obvious not interesting cases for physics. The third case is more interesting. It's tension which is connected with the concentration, and the deformation goes as a sum. In the picture you can see the deformation process and the tension connected with one another. You can see the average tension and the average deformation and the local one. This case is also very interesting and should be considered. These equations describe the average cases with different parameters. It's attractive in point of view of mathematics. You can see that the deformation points are all equal. But we have restrictions anyways. For some good quality materials, it makes sense. These equations are easily solved. And you can see the results, which are described by getting closer. The fifth case, when the strains equal. And here we can have good equations, two of them. You can see them in the picture. It is a well-known law, which was also realized. Case number 6 is not really interesting when the materials are the same. It's about homogeneous materials, which is well known and not an interesting case. The 7th might be attractive. The deformation is related through concentration, and we can see the sum of deformations. Then we analyze everything, and we have the relations which can be further analyzed. And consequently, we have curves which can also be interesting. So we can see these equations which can be analyzed and get interested in terms of physics. In order to undertake an experiment, we mixed different ceramics. We mixed all of them to get heterogeneous materials. Now, in these articles, in these books, you can easily find them and read about them. The following patterns in the classical machine were undertaken, gone through different tensions. One and the same experiment has been done several times. And we also look through the properties It's the particle differentiation in pitch. And it's not always easy to get an equal mix. And in the case of squeezed uh, squeezed constriction, we have two different diagrams. The first one with the second stage, and in the second picture we can see the one axis strain and different patterns were averaged. As a result, what we have, you can see the change of Young model material according to the volume concentration. In this specific case, you can see the growth of the module. In the second picture, you can see the module for aerosol and turquoise, and both of them grow. And the model of squeezed strain. This question has remained open. Aerosol and turquoise are the same material. In other words, it's the same as silicon. So we don't understand why do they all differ one from another. So when we received it as nanomaterial by steaming, then condensing, consequently happens the condensation process. And talking about the definition of young nanoparticles module, knowing the Young model, we have two equations which let this E1 and L1 to define the parameters which we had discussed before. So what do we get? We have taken different averages, and there are the cases number 8 and number 7, which coincide quite well with one another. You can see the decrease of the particle size, and these curves go like classical ones, and the red ones are the experiments shown. As we can see, the parameters of Young models also increase. We, in a way, prove different points of view. You can see getting the particles smaller in size. So if the model increases, then the average numbers of Young model also increases. How does it happen? We haven't solved yet. So consequently, the method of defining of elastic characteristics was given. We got experiments depending on the elasticity characteristics of mechanical mixes, and also according to the experiments, the numbers, the parameters are defined concerning the elasticity of characteristics of nanoparticles according to their sizes. It is defined that for powders of one type with decrease of medium-sized particles, the model Young characteristics go up. Thank you for your attention. Did you define the Young model by nano-identification? We defined by nano-identification as well as by disruption, and the results coincided, which says that we try not to lie. When defining the module Young of elastic characteristics, did you take into consideration the zone and the phase itself? And also, when you defined the elasticity model in strain state, the interface was considered, and we can also talk about including the third phase. But it's not according to definition of Young module. And if we want to get the local characteristics, we need to do that. The squeezed strain, of course, we considered the characteristics. The next report, Valentin Vasilyevich Popov. contact mechanics of clusters of heart cells, mechanical activation and synchronization of myocytes. According to World Health Organization, cardio diseases are one of the highest reasons for death. Thus, it is still in the top of interesting topics for examination. Last year's one of the directions in medicine is local regeneration of cardiac muscle. It's quite hard to analyze this muscle. Microscopic clusters have been used to observe cells of spherical form. And these cardiac cells are grown from stem cells and then analyzed. Last year, I was telling about the reaction of steroids. The original point is considered pluripotent stem cells. They were invented in 2012 by Shinya Yamanaka, who received the Nobel Prize for his discovery. There is a mix of chemical liquids which influence the cell. As a result, the cell grows back into a stem cell. Such stem cells increase and multiplicate in the numbers quite fast. You can see separate stem cells. It's stage number 1. Stage number 2 is stimulation of stem cells back to cardiac cells. And it can be done with the help of specific substances. They develop and clusters of myocytes appear. And you can see that they are alive, real. Stage number 3. These clusters are moved from flat glass to the glass with cavities where they become small rolls. You can see some red spots. It's the microscope can show that they are alive, and the mechanical influence is observed. This is the equipment used. The Professor Nakana has applied. You can see the schematic diagram of this machine. There is a cable that squeezes to the glass plate, and the optical microscope lets to observe the state. You can see this object is quite small and fragile. There are shown the coordinates of an input signal to the output signal. Now we can observe regular reduction. These are just cells, and no nerve impulses are included. If you press too strong, the measurement will increase. If we look into the microscope, we can see the contact and the increase of beating. It's getting strong. Let's go through analysis. The minimum, if we look through the minimum and the maximum of reduction, we can see that the strength is proportional to the degree of 1.5. It's an elastic environment, and the module of elasticity. In the next picture, we can observe the work, the mechanical work per beat. What is the size? Multiply the depth, it's the size of the contact. You can see that the size of the contact depends the energy of the beat. To understand something from the synchronization, we can observe two spheroids. So there is such a specific slot um, where we can put and when it's ready, you can see how they beat independently from each other, and then they relate. There is a slight um, fight, and the stronger they beat, the bigger is the amplitude. Now I would like to turn to the model. I told about this model, but didn't discuss the result. The biological environment can be observed as incompressible environments. If we neglect uh, and if we take into consideration the viscosity, we have a pause in this equation, and they play no role in the viscosity environment. There is a mechanism why the coefficient changes. There should be a negative coefficient of viscosity. Thus, we have the following equation, and we got the common equation with the pause and negative viscosity. We, we can't write down it in a different way. Because here we also have retardation, which is specific for the case. To make them unlimited, we need to introduce non-linearity. And now we can take and make a ball from this environment and start squeezing it. Look what we have got. Now the environment is not quite simple. Luckily, there is a method of dimensionality reduction, which is if we have continuous environment, environment is exact and instead of one task, another can be solved. We can see that the shape is transformed from one to another, and the environment is replaced into the independent areas of springs, and the strength inside of the springs give very exact solution of three-dimensional task. But if it's not elastic environment, then we replace it to viscoelastic materials. And the parameters are definitely correlated. Concerning the synchronization question, if we originally have such a ball, the parameters are independent and each of them is going to violate. They are not steady. But anyways, they are all in different phases. And how does the synchronization work? Easily, if you squeeze them with a layer with a leaf, they will all together move, automatically synchronizing. So all the important parameters are depending on the contact sizes. They function in synchronized state, and it can lead to some tiny movements and to microscopic crashes. And here you can see the direct modeling, how this environment behaves if you squeeze with the growing strength to the slowest to the fastest. And sometimes it happens that it disappears all. Here is the dependence the contact force on the time. It's not what we can observe from the experiment, in fact, but the effect itself leads to the beating, and the details are not quite the same. But we are working intensively with it, with Professor Nakano. Now, let's turn to the conclusions. The first one is basically about the experiments. So cardiomyocytes are a system that works according to some simple rules. When they are formed, for example, in a mutation way from stem cells, they start reducing with frequency of about 60 beats a minute. And for this reduction, there is only one condition, the feeding. Um, the cuts, the reduction itself, don't bring to the synchronization of cells movement, and the synchronization happens thanks to the contact, the interaction with microscopic objects. The second part of conclusions, which is more general, this exact research is part of bigger projects connected with cardiac cells regeneration. The artificially grown cardiomyocytes um, cardiomyocytes principally can be useful for local operations, so-called operations, to improve the defected cardiac muscles. As well as these, the different research made by the Institute of Max Planck in Munich show that the same processes of regeneration happen inside a human body as well. And it was discovered that the factor which leads to despecialization of stem cells, it forms myocytes and which can be created by immune cells. And in comparison with green tritones, regeneration happens at 100%. We need to also take consideration timing frames and the formation of stem cells into cardiac cells takes about 2 weeks. So patience is the key to the work, to the processing of this experiment. I would like to finish my report. Thank you for your attention. When you were telling about the model, mechanical model, we don't pay attention to the presence of the model. And concerning the mirror, to have an effect, we need to change the sign of the main members, and we have unsteadiness and the final amplitude. To realize, we use the elementary methods. When the cells stop reducing, is it the end of the cell life? In this case, there is no end, there is no death of the biological death of the cells. Non-lineation works this way. And if you press it with effort, how long is it going to work? As long as it is fed. There is also an experimental research which shows that very small agglomeration of cells do not cut, do not reduce, and the small size is considered 4,000 cells in one cluster. In your experiment, the strength is the key to synchronization. And what about natural cells in the natural heart? I could speculate, but I'm not going to do that. So heart is agglomeration of the cells, and now it starts processing as a whole, as a muscle, according to the electrical impulse. So does this impulse work as well as mechanical in these experiments, or another way? What is your opinion? Yes, surely it's a basic fact that there are electrical chemical impulses which brings to the coordinate work of the whole body. The peculiarity of this study is that it has not only electrical chemical but also mechanical influence. So the fact of pressing brings to the beating. Nevertheless, what do you think? Why is it unsteady? Why does the amplitude happen and the violations happen? Why does it violate? It's a question about the mechanisms of negative viscosity, why it is unsteady. There are answers to these questions as well, but in the frame of this model, it doesn't really make sense. It's a question about why this cell being deformed starts deformating. According to the literature, there is energy savings for processing of this system. You said that the considerable amplitude occur with frequency of 60 beats per minute. So when does the collapse happen? According to this experiment, the collapse happened at about 120 beats per minute. The further decrease of amplitude goes up to 600 beats. In fact, we have several different models where you can find these gaps too. Mm. Yeah. When the frequency increases, then we can see the increase in the amplitude of oscillation. Можно дышать.
From beam. That means the materials fed directly, not like SLM. Of course, I did some SLM research, but not the focus today. We can compare the direct deposition technology. You can see like laser, electron beam, and arc. For the efficiency, I think arc is the most high. It can be to 30 kilogram per hour. It's about 10 times for SLM. Most importantly, for arc method, we can use a wire, powder or something. It's equipment and material is far low. It's far low compared to the SL method. So that's why I focus more on arc or laser direct deposition. Okay, second part, what we did on EM in my lab. You can see some machine and products we did. It's a plasma printing machine with a robot. You can see we have 2 wires. We can use 2 wires or 3 wires. Not in this picture, okay? We can another external wire feeder. But this one you can see we can 2 wires can fit same time. And it's hot. We can hot it at the same time. It's a hot wire, okay? Also with some ultrasonic vibration on the sample. This picture is our self-developed software. We can choose the parameters. We can set the technology by the computer. This some products we print by this machine with different materials. We print this shape products with HEA, high entropy alloy. I think it's very less fun. And this one is about 1 meter. 1 meter is a product for some special application. It's not by HEA, it's about aluminum. We also have some plasma powder feeder materials. It's not the key. The key is we also use the ruler. We can print and then ruler together. So make the mark structure or the grain size smaller, fine. Okay, sorry, the color not good. But this way we can, the color is also some data we cannot see clearly for the background color, sorry. But by the yellow one we can see, compared to cast or other material, our work is promote greatly, especially the elongation. Also includes the tensile strength. It's another technology we use in our lab. It's a CMT, cold metal transfer additive manufacturing. But this way, we can print some like the non-ferrous materials, like aluminum, titanium, something. So it's one example we print in our labs. Also, we did a laser direct. It's also some sample. We have SLM, but we today we usually are mainly introduce this. But this one we can print as a sample, like we made some products for local companies on the surface coating. We also tried the HEA material. We get the hardness more than about 1,000 HV. So it's have applied in the local company. It's very interesting. Okay, today I will introduce the work one with the wire-based AM of HEA, because we know for HEA it's very expensive. We use a lot of elements. So we traditionally we do the new material by experiments, but it's really money burning. So before we do it, we will design the material, design the composition by the software. It's an example, okay? Then we predict its properties by machine learning. So for example, the hardness, the mark structure. Here I give an example for two materials, two types. One is about BCC plus FCC. We can see our prediction error is low. It's about less than 10%. Okay, wire-based AM or HEA. That means we use wire to as the material to do the AM. This is a paper published by the Tennessee University from USA. It uses wire. It's a single wire. So first casting, then hot isostatic, and maybe heat treatment, then to the billet and extrusion, something. So it's a very complex technology. Most importantly is what? It's also in the cast. So segregation also happens. So that's why we use this technology. It's called combined keyboard wire. We first published, I think our group is the first one to use this method to make products and publish the first. In this way, you can see a lot of keyboard wire. The keyboard wire we have a lot of types, like 3, 5, 7 to 14 something, and with different technologies, the distance with one twist space, it's totally different. Okay. Also, you can see from the high-speed camera made for the keyboard wire, when it melt, the wire will have a self-rotation, which is very good, especially for HEA, because I say this have a segregation. So we can have a stir or make the composition more evenly. So we use it like this in the paper. Okay, the twist wire is made by 7 single wires, and the composition is controlled by the diameter. So that's why that's what we did. For the property, you can see it's I think it's good. The compression property is about 3,000. Oh, it's 2.8 thousand megpa. Most important with a good elongation property. So compared to other way like casting or something, it's better. It's better, especially for the XMP. For the mark structure, I think it's simple, not so complex. Okay, it's mainly from BCC, FCC, and plus some precipitations. It's also we also did the heat treatment. Like A, B, C is about different temperature. Okay, I will for time limit I will introduce shortly. So the precision will change with the heat treatment temperature change. Okay, We also make the nano hardness on different way, like the BCC, FCC. We can check which one dominated the properties. Okay, quickly. Heat treatment, the different. You can see the hardness for the 600 is better. 600 is better. Okay, see the picture. Okay. So why it's what happened? You can say for the heat treatment, the mass structure change. Mainly some precision happens, like the L1, 2, and the sigma phase changes. That's why the hardness and the properties change. We can also use the double wire, with one is the cable wire, one is a single element wire, because like aluminum have a bigger effects on the mass structure. So we can change the aluminum composition. From the picture, we can see from top and the middle and the bottom, the aluminum composition different and the mass structure totally different. You can see the picture is more clear. We can say it's okay. We have no time. Okay. For the picture, we can see the change from BCC, almost all BCC to almost all FCC with aluminum change. We also use the plasma. Okay, the wire, we can finish it. The second is about the powder plasma arc. What we did, what mainly we because a Nature paper introduced the strengthening mechanism is mainly by the different element diameter, and we analyze it and say maybe it's not the main reason. Firstly, secondly, like the this element is very expensive, so we wish to use the cheap one. So we substitution of the TA atoms in high entropy alloy. By this, we can get the simple. Okay, the principle is the same crystal structure, similar element distribution, similar mass structure, and the same crystal rotation. So we can say the mass structure changed with the replacement of the element, but it's the property is similar or even more. We also test the top, middle, and the bottom parts have the property, but what's the advantage is the cost. We cared cost. The cost of placing the elements was reduced by 29%. And also we proved a strengthening mechanism is not by the diameter, it's by the solution way. That's why we designed the experiments and do it. Okay, the conclusion is we use a new type of combined cable wire can additively manufacture big size HEAs, high entropy alloys, and has the advantage of high efficiency with less or non-segregation and better mechanical properties. Second, cable wire plus a single wire is a dual wire can control the FCC and BCC composition easily, and maybe I think maybe precipitation. Some functional HEA were successfully also fabricated. Third, arc additive manufacturing through powder can more easily control the composition of high entropy alloys because we can change the powder composition for the wire. It's harder for that because we mix the wire and twist it together. Fourth, the laser direct deposition can also fabricate a big size HEA. Powder requirements are necessary because he has special requirements for the powder size, the powder shape, something. Okay. But for time limit, I did not introduce the laser juxtaposition. We also did a lot of work on that.
Yeah.
Okay, I have a very quick introduction of my recent research. Most contents from the published papers are listed 10 papers. If you are interested, you can find the papers for the details, or you can contact me.
Thank you for interesting information.
Okay. So this work is supported by some fundings and also from international collaboration. Like for my group is some international professors, including some from Russia. Okay. Thank you.
Thank you. Dear colleagues, questions, please.
Was scheduled to stop at 12:30. Okay.
So thank you for your presentation. I have a following question. High-entropy alloys have excellent mechanical properties, but what can you say about the diffusion properties? Is the diffusional processes fast or slow in such a material?
So the voice not so clear. It's can you repeat your question? I just say some mechanical property or something. Or what's the question, please? Sorry.
The question is, are the diffusional processes fast or slow in high-entropy alloys?
Fast.
Is diffusion is fast or slow in high-entropy alloys?
Sorry, I'm not. Sorry, I did not get the point. You mean the future or something?
Can you repeat? Future?
Or you can type.
Переводчик поможет. Диффузия в интерметале.
Diffusion.
Oh, diffusion.
Diffusion.
Diffusion. What does it mean? Sorry, I checked the.
Пусть ответит.
Diffusion, right? Oh, you mean the elemental diffusion or something?
Yes.
Oh, okay. I get point finally. Okay. We did not purposely focus on the diffusion, but it is because for the HEA, one character is low diffusion, right? So because a lot of material mixed together, so it's hard. And for the AM, SNKX is harder because it's a high rate heating and high rate cooling. So the diffusion not so much, I think.
Thank you.
For AM.
I got it.
Okay.
The next question. I have one question.
Okay.
Could you show some details which you made for something, details for aerospace, maybe shipbuilding, or maybe
what kind of details? The product or process or something?
What kind of details? Yes.
I think I have one video here that I showed. Like in my lab, like this. So it's always made by my students or myself. This one is also like we make in the computer, make the products pass, and then use print it out for HEA or other material. This one not HEA, but it is the same way. I remember this one is like HEA, one type of this. So it's by layer, I think it's like this. Yeah, layer by layer size is brought. I'm not sure.
Are these details tested maybe in the practical usage?
A practical usage, I think.
Natural.
Yeah. For HEA, I think the application is not so broad now. It's a problem. Yeah, it's a very good question. For the application now, I think for the coating, for some like in Wenzhou area, we have some valve company, so we can like the surface make it very high hardness and some corrosion resistance. Okay, for products, I think I make only two. One is by this, one is in some like shipyard. It's on not a big number application, but we use it in some small batch for testing. It shows good.
Thank you very much.
Okay, thank you.
Следующий доклад у нас делает Валиев Руслан Зуфарович. Объемные наноструктурные материалы для применения.
И с другой стороны много открытых вопросов. Я постараюсь продемонстрировать это. И это, так сказать, и требуется усилить коллаборацию. Я думаю, что вот эта конференция, замечательная конференция, поможет это сделать. Но я представляю две организации, две лаборатории, два коллектива. Это Институт физики перспективных материалов, ИФПМ тоже, в Уфимском государственном авиационном техническом университете. Второе – это лаборатория механики объемных наноматериалов в Санкт-Петербургском госуниверситете. Эта лаборатория была создана в рамках моего мегагранта. Он уже закончился, но в этом году мы выиграли с китайским профессором Ли мегагрант снова. Значит, эта работа продолжится, но уже с фокусом в основном на биоматериалы. Но вот тема, которая сегодня прозвучит, она была впервые выведена так на дискуссию профессором Ростиславом Александровичем Андреевским, который написал такое небольшое учебное пособие около 10 лет назад «Наноматериалы на металлическом».
It's a very exciting and intriguing book by Andreevsky, showing that nanomaterials can have stiffness and strength and work in different environments with erosion, which happens according to radioactive and corrosion requirements. So it's a book review which is devoted to nanomaterials. My report is going to be devoted to the materials with intensive stiffness. So we are going to talk about ultra small grain materials and then a new direction nanostructure in metals, alloys, and to discover how it cannot be the basis of new properties, multifunctional properties which can be opposite, like strength and elasticity. But at the same time, we lose the elasticity. So how to combine these? The physical properties of electrical transfer, and it has a big innovative potential. So first, about the classification. So the size is 100 nanometers and less. And the bulk nanomaterials can be not only in centimeters, but also meters. It can be 500 nanometers, and there are other nanoparticles with segregation on the frames of grains. There are two approaches known as for nanomaterials. It's obtaining nanopowders. There are a lot of studies published. So it's about the way of making the grains smaller. This intensive deformation is a work according to the equipment realized by the Professor Bridgman. He was the first to combine the high pressure and big deformations. So he made such equipments, and he was the pioneer in this field. So the original materials that are transformed later happen 100,000 times. And this is the principle of intensive deformation. And the result is getting ultra small grains. And there are different methods of intensive plastic deformation. It includes hundreds of works connected with the high pressure and it's a continuous process as well as other methods. There is no mass usage for that, but the scaling is also approaching. You can see the computer modeling of the given processes. Although obtaining of small grain structures, it's also a system which includes low temperatures and safe deformation can go up to 6 to 8, without which we cannot receive such deformation sizes. And another one is turbulence. So in spite of non-monotonous deformation, we can get the materials Such principles were published in the scientific magazine Progress in Material Science. So you can see the links used from this only article in 2022 going up to from 5,000 to 5,800 usages. So the term may sound simple, but the elastic or plastic deformations conducted by professors of mechanics show what is common and what is different, and intensive deformation and general deformations. So, from the point of view of mechanic discussions, we can see that the same method can be an ordinary deformation. It depends on the geometry of the given environment. So there are big and intensive deformations. So we show the experimental and theoretical results in the process of rotational deformations. So for the last 10 years, the influence of intensive plastic deformation is huge on the evolution of microstructures. There is a formation of ultra small grain structures as well as irregular phase formations. Amorphization and nanocrystallization, as well as observation of secondary phases and dynamic aging. So some examples of unusual phase transformations. So on the right, you can see the melted, absolutely melted cement carbide. And the structure of high carbohydrate steel, the dynamic aging, we take alloys as a pattern, which allows to use the methods which are unfortunately a little problematic in Russia, ion microscopy shows that. So we researched the aluminum alloy, and we can see the segregation on the border with a size of 3 nanometers, and nanocluster as well. So there are nanostructural defects with a high stiffness, and a very famous alloy 7075 alloy. So it transforms as a form of segregation at high temperatures. You can never find structure like this. And when we can find not only such nanostructural architecture and also nanomorphic areas, which allows to get new structures of metal materials and to transform them into unusual structures. So we can see the grain-bordered transformations happening at the normal temperatures and varying the mechanisms of deformation. We can offer specific properties and some examples of its development. How to receive high strength material. So it's a combination with elasticity. High strength used in different conductors. So talking about ultra strong materials, when changing from microstructure to nanostructure, a dependence between the distances from the size of the grain is observed. It's a decrease, it's a negative experience. But we can go to theoretical strength of the material. We can combine the mechanisms. So we have nanoparticles which can regulate the volume. So if we manage the structure of the grain borders, we can get the 30 or even 50% of strength increase. As a result of intensive plastic deformation, the alloy 70,000 demonstrates the viscosity frame. These are realized on steel material, ultra strong, and elasticity in materials. We usually lose the elasticity of ultra strong materials, but we can also control the speed of the movement. For aluminum alloys, it's a cycle. You can see a super thin layer. So you can see phases of aluminum and zinc. And we can include the Pascal's mechanism. It is known that there is the effect of ultra strong elasticity and the connection with high temperatures and low temperatures. How can we increase the speed, decrease the temperatures? Through the structures, through the segregations, and in fact it works. So we have been recently working with our Japanese colleagues, and we can see the percentage of strain. It's a zinc alloys. It's hundreds of percent of deformation, obtaining the grain. And the next topic presented is the combination of stiffness, the nanostructural, which allows the unusual structure to form the size of grains, nanoparticles, we get a combination of high strength and electricity conduction. So here is the graph of the dependence of electricity conduction, the choice of conductivity. It's a compromise between mechanic properties, electric properties, and others given. And talking about the extreme conditions, it's radio resistance. As for the swelling, it's proved with different researches. Such as X-ray or it matters in different mechanical properties. It can matter in medicine. We can get we have a technology of getting a high strong titanium using the intensive plastic deformation. It's also creation of new dental implants from nanostructural titanium. Now it is replaced to nano-magnesium and new implants from magnesium, from zinc. These are no titanium materials. And one of essential discoveries of our young colleagues is its increase of erosion titanium alloy characteristics for avia engines. So without protection surface, this problem is not solved, but there is the new point which says that when we decrease the mechanical properties and it leads to decrease of resistance to erosion wear, and the erosion resistance grows almost 10 times. This is the way to very big high strength. And of course, it's a realization in industrial modifications, in pressing, and its leaves. So the conference in Bangalore is getting started finally, which is Nano SPD 8. Indian Institute of Science is the best institute of innovative science institute, and we have invitations to take part, to actively take part in this conference. There will be a separate section in this direction, and the second one is the world interest. Among the list of material science professors, our Japanese colleagues have made up the reviews of historical developments and recent advances. So many scientists published some articles there showing the way it develops. So for the young generation, it can be interesting how and where it develops. Thank you. Ну, ставьте. Сейчас надо, да? Ой. The next speaker is Polyanskiy Vladimir Anatolievich with the topic using the models of boundary layer in solids to predict plastic deformation and fracture of metals. Dear colleagues, I'm happy to welcome you offline, and I am glad to make a report and to more detail tell about my research. At the moment, the Institute of the core of our scientists are mechanics, people who understand the world according to the deformation, speed, and trying to explain the world with the help of logical models. And my report is going to explain how it can be used, applied in real life. So the relevance. What is the problem of modern industry? The high strength materials that you have heard a lot of different reports about, the beginning of this day. They are widely used in industry already, as for example, the body frame of the modern car consists of 70% of high-strength quality materials. So this body frame protects in case of a crash. Another example is gas tubes. So we can see the highway gas pipeline, and this consists of 100% high-strength materials. A big variety of experiments have been conducted to get this result. Similar comparisons can be seen in the pictures. In the airplanes, fuselages of the airplanes, it's about 2,000 megapascals of steel. In spite of high-strength materials, they are resistant. So, for example, talking about airplanes, after each flight, one needs to analyze and observe the protection rate. Now, the same situation occurs with gas pipelines. So they used to be controlled. Nowadays, hundreds and thousands of kilometers can be destructed and blown. And for example, in cold deserts, in marshy plains, it often happens in modern days. So the real strength doesn't grow, and the count on the definite stiffness that the engineers make appear to be very dangerous. Like at the railways, there used to be the wagons valid for 30-35 years, and nowadays, because we use higher quality metals, for instance, we replace with a better quality steel, and they start destructing. So you can see the unpredictable blowings happening last years. So it's well known that at plastic deformation, you can see the 5% of deformation of alloys. And you can see the appearance of plastic waves. As an example of indium ilium stannic alloys. In comparison to the stiff waves, the plastic waves have the opposite reaction. The bigger is the strain, the fewer plastic waves appear on these areas. So it doesn't match the dynamic imagination about the stiff bodies used in different form laws. One of the reactions is the effect of Portfin-Leschev K.A. At the beginning of the 19th century. It includes the information that some alloys, for example, magnesium, aluminum, and zinc alloys, the deformation happens bit by bit. First, it's gradual, and then it becomes abrupt. Here you can observe a lot of different patterns. Now in Perm, there is Trusa School, where scientists analyze this topic. Basically, Ilyushin related these waves with stability laws, and there is the viscosity in materials and deformations in them. And so these explanations can be criticized because when we take the curve of deformation, we have the phenomenal explanation only. And there is a big number of works devoted to the explanation of these plastic waves. You can see the dislocation. The problem is that each equation includes 6, 7 or more parameters which are not really implied. And I would like to lead you to the results that we have discovered. So the plastic waves cause wave acoustic anisotropy, which is used for controlling and measuring the tension. So you can see the equipment used for it. So you can see that the whole material is going through plastic deformation, and if we polish about 150 microns, 500 for aluminum, all these waves will disappear. And so the surface layer, which defines plastic waves, is closely related with hydrogen reaction in the thin surface layer. And you can see the surface effect, which influences the flatness of deformation. In this surface layer, you can see the crack formation, as well as black holes formation, pores formation. In a Lochin's book, you can find about 700 works on this topic. So there is a surface layer with a depth from 10 to 100 micrometers. Now, which depends on the size of grain, but it appears even on monocrystals at plastic deformations, and this layer defines the behavior of the material when the deformed deformations happen. And we have discovered that there is a border layer appearing when filled with hydrogen. And the pattern center is plastically formed. The simplest model known from 70s of the previous century. So a quick review of these results. Thanks to the layover of hydrogen concentration, we have two areas. The area of viscosity destruction and the foam content. Similar results have been received for tasks of heating metallic and cylindric patterns. And the next model used of polar environments. It is connected with the turn of grains with classical deformations. We supposed that the turn of the grains can be explained by very stick slip movements and change, which are connected with the borders. The similar models which have been used allow us to describe the wave process and in fact to receive a separate wave which appears at the surface layer, which can have decreasing solution, which can break to stick slip increase. The second interesting question is the influence of the grain size. The simple model which allows to include the surface strain. It appears that we can get strength of steel according to the size of the grain, which is brightly shown in this picture. Thus, the surface effect allows to describe the strength of real materials used. And the last example, this area between A and B, it is observed that many curves of load. We can describe it according to the dependence of viscosity. The grain size, in that case, the plastic deformation, we can get chessboard which will be connected with practical viscosity of grains, which can start plastic deformation. The main conclusions that I would like to draw, of course, one of the main and essential deal is working out and realization of strong elastic materials. But now we know that the surface layer defines the strength of the material, and it is quite restricted. It should be researched and we need to take into account that point. Thank you for your attention. Thank you for the interesting report. I have a question to the beginning of your presentation. You were talking about strength or destruction. I agree with you, there are differences in terms, but we need to define if there will be a destruction of screw or not. There is a cycle load. So the influence of hydrogen starts also with the surface layer of the material. And it crashes at experiments with fatigue strength. about 10 microns modifications of surface happens. Thus, the depth of the surface layer influences on the strength of the material a lot. So the mechanics doesn't solve this problem because the area of this depth is equals 0. we would like to present our partners report, the company of Fianum Lab, about advanced solutions of the Russian manufacturer Fianum Lab LLC for analytical and research laboratories. Good afternoon, dear colleagues. I am the head of the company Fianum Lab. We help you, our colleagues, to solve your relevant tasks. Our main directions are the system for tribotechnical analysis, for different experiments with friction and wear, its analytical systems, chemicals content, its devices for scanning, optical microscopes. Also, we have additive technologies, which was opened last year. It's 3D printers, titanium and aluminum, all of the Russian production. And we have another direction is oil and gas industry. So a short review of our profile, and we will be happy to see you observing our stand in the hall. So first of all, it's universal tribology, everything connected with the experiments, which is connected with rotational schemes, high temperature models, pin disks. They allow to model any pairs of friction. In the contact zone, you can make any high loads, different settings, as well as additional modules, and transforming in vacuum. It's quite an exotic requirement for the space structures. Loads starting from micro, when we can see adhesive surfaces, for example, to the extremely high loads in the contact zone, as well as ointment materials and high frequency experiments and shear testers and ball testers, various instruments, and interesting tribometers, especially, for example, this equipment is called rolling friction twin disc. It's about contact resistance, contact where it is working with the railways. We have an equipment called Eurasia. It's so-called table stand equipment. Another machine that can be interesting is the high frequency experiment machine, with a high frequency, high temperature, about 800 and even 1200 degrees Celsius. It can be attractive for aerospatial industry. It's closer to the aerial building branch. Any kind of tribology tasks can be solved with the help of our equipment. In the slide, you can see simple regular machines. It's for studying and research tasks, depending on the budget and the technical task. You can find the equipment necessary. A new direction in the relevant reality, its localization of spectrometers production. So originally they're Chinese, and we improve them, develop them. We develop the program software according to the task. You can see atom observation spectrometers, as well as optic spectrometers. As well as scan microscope. Although they're produced in China, the microanalysis details are of imported production. Optical microscopes developed in Russian lab. As I have mentioned before, 3D printers, metal printing. Can pay attention that the working area is from small lab equipment up to 800 millimeters and even more. Different metals can be used. Now we are producing wheels in the laboratory system. You can see it alive. If you are interested in additional information, you can come to us and we will give you some additional information. And another part of oil and gas industry is viscosity tester, everything connected with modeling of bitumen and paraffin formations. We have an agreement with a German company, and so we have worked and we are working now with the components composed here in Tumen. We also make our radiomagnet resonance machine. To determine not only organic substance, but also the parameters which are mainly important for oil receiving. This is all. We will be glad to see you at our stand and answer any additional questions and solve any relevant tasks. Thank you for attention.